All right, it ended up being a nice split with what we did the other day because the next module is all about probability rules. So there are a couple of like introductory rules in this beginning probability module. So events and its complements. This is something that's super easy, and you probably have seen it before, but we will talk about it real quick here. So Yolanda works as an IT technician for a local company. There are 994 computers that are not infected with the virus out of the company's 1,000 computers. Yolanda chooses a computer on the company's network at random. Let A is the computer is not infected. B is the computer is infected. So the probability that you pick a computer that's not infected is 994 out of 1,000, which is 0.994. That's the probability of A. The probability of B is the complement. There are two different ways to do this. The complement is just the opposite of that. So if that's 99.4%, let's just say it's 99% for easy math. If 99% of the computers are not infected, how many are infected? 1%, right? Y'all know you just do 100% minus 99, that's 1. That is what the complement is. So the complement is 1 minus that probability, and it would give you that answer, okay? So 1 minus the probability. So it's just like 100% minus whatever percent that one is, and it would give you your answer. Like y'all know, like in your head you know that. That's just called the complement is what that's called. For the probability of B, the two different ways to do this is you could do 1,000 minus 994 is 6, and then 6 divided by 1,000 is 0.006, or you could do 1 minus 0.994 is 0.006. So either of those would work. So you can kind of do the complement of the total minus what you're looking at, or you could find the probability first and then subtract it. It kind of depends on what's easier, what the problem's asking. The next one I have here is identifying independent events. Ooh, they've changed this way, the layout of this one. Did my cord? I'm scared this cord's going to break. Independent events are the definition of independent events. I need somewhere to write this, I guess, but the definition of an independent event are the probabilities do not affect each other. And I went on a rant in my last class about I don't know English, so I don't know if it's effect or affect. Probabilities do not affect each other. Y'all can tell me if it's affect or effect. I don't know. English is hard for me. What we're going to start looking at, though, just like the complement, you have the first one of the event, like event A and event B, so you got multiple probabilities here. So you have to say, if I do this probability, if I do this, does it affect the change of probability of this, right? Okay, so there's 20 of y'all in here. If I randomly pick one person to come up and work the board, or work a problem on the board, if that person goes back and sits down again, and then I randomly pick another person, I haven't changed the probability. The probability that you get selected is 1 out of 20 still, right? But if I have that person come up here and they do the problem, and then I have someone else come up here and do the other problem, I've changed the probability because the first person that comes up is 1 out of 20, but now that person's already up here, so the next person that comes up is 1 out of 19. So you kind of see how it changes. So they call that replacement. I replace the student back in, right? So the replacement is independent, and if you don't replace, it's dependent, okay? So here a hat contains the slips of papers, and the key word there is that replacement word. A hat contains a piece of paper with the boys and girls name of the class. A student is randomly selected and then returned to the hat. So I do not, the first selection is a boy. I return it to the hat, so I have not changed the probability. A bag contains the marbles and deep orange marbles. The marbles randomly selected and then set aside. So that is going to be dependent because I've changed the probability when I pick the second marble. Does that make sense? A deck of 11 cards labeled 1 through 11. A card is randomly selected and then returned to the deck. And then I pick again. So I replaced it back in. I do not change the probability because I did not take anything out. Here is the weird one. This is the weirdest one. A family has 2 children. The older child is a girl, and then both children are girls. This one you just got to think about. In order for both children to be girls, doesn't the first one have to be a girl? So that is why this is dependent, because the second one can't happen unless the first one happens. Okay? Both can't be girls if the first isn't a girl. Okay? That's kind of the weirdest one that it has on here. Every other one just has to do with the replacement versus replacement. A number of dice is rolled 1 through 6. You roll it twice. The die never changes, right? Like it's always 1 through 6. So I can't remove a part of the die when I do this. Okay. So the die never changes. So that would be independent. We in this class deal with independent a lot more than we deal with dependent, because when you start doing dependent, it gets hard when you start changing things like that. So you won't see independent very often in this class. Or I'm sorry, you won't see dependent. We stay in the independent world. Relative frequency. So this is a terminology thing. We talked about relative frequency way back in like the second module maybe. But relative frequency, they use this word when we talk about different tables and distributions. Relative frequency, when we said it way back in module 2, we said it has to do with the percentage, but our percentage is basically a probability. So all those words are very interchangeable. It's just how you talk about them is the way which one you use. So what is the relative frequency of the adults who sampled who are not registered to vote and prefer to obtain their information through TV? So TV and not registered would be this one right here, right? So you have 20 is the number we are looking at. And then you go back and look up here. It's a sample of 255, so you don't have to add up all those by hand. It usually tells you what the total amount is. So 20 divided by 255 is 0.0784. So it's just 0.08, I guess, if I only got to round to 2. Okay, so the relative frequency is just the probability, but this is called a two-way table. I didn't talk much about that. The two-way table, this is used a lot, a contingency table or a two-way table. It gives us a lot of information. So we can do registered and non-registered, and then you can do where they get their information from. You could like do freshman, junior, sophomore, seniors, and like male or female. Like you can do all the different two-way tables. So you can have columns and rows, and we will use that a lot coming up. Let me make sure I save this real quick, because I actually did that the other day. I didn't save it. No. Probabilities of draws with replacement. Not sure why that's next, but that's fine. So a fair die is rolled 5 times. What's the probability that a 4 is obtained on a... Oh, man. I do not like this problem. I know how to do it. I just don't want to start with that one. Okay, so that one, we'll come back to that one. I'll find it in just a second. A urn contains 5 pink and 8 white balls. 4 balls are randomly chosen from the urn. That is, each draw of the ball or with replacement. The ball is returned to the urn. What's the probability that all 4 balls drawn from the urn are pink? When you start getting into these multiple probability things, take it one step at a time. So I want to know that all 4 are pink, okay? So the first draw that I have here, well, first of all, let's figure out the total. 5 pink plus 8 white would be 13 total, right? Okay. The first draw that I get a pink one. So if I have all 13 in there, I'd be 5 out of 13, right? So that's the first time I draw. Now I put the ball back in for my second draw, and when I put it back in, it doesn't change. It'd be 5 out of 13, right? The third one, again, would be 5 out of 13. The fourth one would be 5 out of 13. When it doesn't change, you could actually just do it to the 4th power. 5 over 13 to the 4th power. because you're doing it 4 times. But what you want to do in these is just think about a single event. Think about the first one. What would happen? 5 pink ones out of 13 total. And then start thinking about each one. So your thought process should be on the individual draws. So let me do that in the calculator real quick. To the 4th power, 0.0219, something like that. I guess if I got to round to 2 decimal places, it'd be 0.22. Now I got to go back and find that hard one. Do they do one without? Oh, this is always replacement, right? Okay, I really hate that hard one because there's an easier way to do that. This one's not hard, but a fair die is rolled 6 times. What's the probability of having no 3 or no 6 among them? Like, don't think about 6 times, right? How many, a 3 and 4, number 3 and 4 would be 2 sides out of the dice, right? I don't want those, so I want the other 4 options. So I have 4 options out of 6, right? So I do 4 over 6 to the 6th power. And you can do 4 divided by 6 is 0.67 to the 6th power and get your answer that way as well. Oh, come on. They're not going to give me that hard one again now? There it is. All right. This one hurts your brain, but this is one of the reasons that we're working ahead a little bit, because this thought process is something that we will use a lot in this class. Okay, a fair die is rolled 5 times. What's the probability that a 4 is obtained on at least 1? Okay. If I roll a dice 5 times, I could get a 4 0 of those times, 1 of those times, 2 of those times, 3 of those times, 4 of those times, or all 5 times, right? Like, that's my options. I could get a 4 those different amounts. If I did at least 1, I would have to find the probability for this one, this one, this one, this one, and this one, and add them all together and work it out separately. That's not fun, okay? But what do I notice about that? The only one that isn't at least 1 is a 0, right? So the thought process here, and stick with me for a second, the opposite of at least 1, or maybe I shouldn't use the word opposite. How about we use the word that we just learned? The complement of at least 1 is none. That's a little weird to think about. Oh, come on. Okay? That's a little weird to think about, but the complement of at least 1, the only other one that's not due is if you got none of them. So what would happen if I got none of them? All right. So let's think about that answer, and then we can do 1 minus that to figure out everything else. If you see this at least 1, there's an easier way to do this, but we'll talk about that next week. All right, so what's the probability we get 0 4s? Well, I would get any other number on the dice besides a 4, okay? The opposite of getting a 4 is not getting a 4, right? So that I could get any other number on the die. And I would do that 5 times. So that would be I'd get 0 4s out of 5 different rolls. So 5 divided by 6 to the 4th power, to the 5th power is 0.402. That seems high. No, it's not, I guess. Okay. So that's the probability that I don't get any 4s. So the probability that I would get at least 1 would be 1 minus that number. 0.598, and that is my answer. So on this situation, it's easier to find the complement of it and to do 1 minus. That 1 minus thing is a big thing that we do in statistics. By the way, you can do this all in the calculator at one swoop. Just to show you. When it says at least 1, I'm going to do 1 minus, and I want to find the opposite. So 5 sides that don't have a 4 on it, and then take that to the, undo this button, to the 5th power. Okay. You can do that all at once. So when you're trying to find the opposite, you always do 1 minus. That's the big thought that we have in stats. Odds. I'm going to solve it real quick just so I have it right here. So probability are a little bit different than odds. Odds are always in favor or against. So in probability world, what we've been doing is, I guess, I always say what you're looking at, but it's the event. What you're looking at divided by the total amount, or the event divided by the total or sample space. What odds are, odds don't do the total. They say what's your odds of winning. So it's like what's your odds for divided by against. Or what's your odds to win versus what's your odds to lose. Something like that. Okay? So Rita's playing a carnival game. There's 12 balloons. They got small, medium, and large. 1 small, 2 medium, 2 large, 7 extra large. She hits one of the balloons at random and wins a stuffed animal of that size. Find the odds of winning an extra large stuffed animal. Okay. So what we're going to do is look at XL versus not XL. So there are 7 XL and there are 5 that are not XL. Okay? So you don't do odds out of the total. The probability of getting an XL would be 7 out of 12. The odds of getting it in favor of getting an XL would be 7 out of 5 because you do the 7 versus the ones that aren't. Now this one said in favor of. The next one says against. Oops. The next one says against. So that one just flips it. You would do what's the problem of not getting an XL over the getting an XL. It would be 5 over 7. Okay. So you can always like to check odds. If you have A and B, A plus B should always equal the total amount because it's your favor and against, or against and favor, whichever way you're looking at it. But they should, like 5 plus 7 equals 12 because there's 12 total balloons. We do have a dependent one right here. We don't do too much. All right, back to the deck of cards. Deck of cards is just easy to talk about in probability world. This is an independent event, so this is going to talk about replacing it, I'm guessing. Deck of cards has 52. Suppose a card is drawn at random from a deck and then shuffled back in, so that is replacing it. Then a second card is drawn from the deck, and it's shuffled back in for a third time, and then you shuffle a draw. What's the probability of drawing a black card, a jack, and then a red? Okay, so we have 3 different things we want to look at. A black, a jack, and a red. So a black card is, there's 26 out of 52. Okay, we put that card back in so our total does not change. A jack, there are 4 of them. Okay, a red, we put that card back in so our total does not change. Okay, find each individually and then you multiply them all together. All right, I'll do this on my calculator here, but then I'll show you how to do it on the Alex calculator real quick. Should be 0.0, what do I got to round to? 4 decimals? 192. Okay. So this one is always going to be the total out of 52 because you put it back in there. In the Alex calculator, you can do fractions. So 26 divided by 52 times 4 divided by 52 times 26 divided by 52, okay? So you can just write it all out like that and get your answer. So use the calculator for that, and that's easy. The next one is dependent events. So I'm guessing on this one, they are not going to put the card back in. So a card is drawn from random at the deck and is not put back in, and then the second one is drawn and it is not put back in. Okay, we're only doing it twice this time. So what do we got here? A face card and a second. The second card that's drawn is a 2. Okay, so we have a face card and then a 2. So my face card, how many face cards are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 52, right? I don't put that back in the deck, okay? So there's only 51 this time. And now I have the 2s, there are 4 of them. And then you multiply them. So think about your face cards. You don't put it back in, so you do 4 out of 51. So 12 times 4, divided by 52, divided by 51. Should be, is that like the same number? I guess it's not quite the same. Wait, it's 4 decimals. 0. Oh, that was 4. My bad. So again, in the calcs calculator, you could do, what was it, 12 divided by 52 times 4 divided by 51. Okay. So it's nice to see it because you can just see it all in the ALEKS calculator at once, and you can see, okay, there's my first draw, there's my second draw, and you can see that number go down. If you did 3 cards, it'd be 52, 51, 50. All right, that finishes up that